Hello, everyone. You hear me, I suppose. I'm really glad to be here. After all, the pandemic and everything. This is actually my first conference. I was supposed to do one a couple of weeks ago, but I got sick, so this is the first one I'm doing in three years or something. So it's great to be here. I don't know which in order, the time I'm actually here speaking at GeeCON, but the conference organizers have been really gracious inviting me back. The last 3 years we've been working on something quite interesting, I think. But first, who am I? I'm Jonas Bonér. I'm the CEO, and founder of Lightman. I also created the Akka project about 13 years ago now, in 2009, and a lot of my life has evolved around distributed systems and working with clients using Akka, and also working with clients, using things around Akka we've built, and before that, other types of distributed systems projects or products, trying to move to the clouds, struggling with those things, etc. And lately at the edge, which I'm going to talk a little bit about as well in this talk. So it's the title is Extending Real-Time Data and Compute to Cloud, Edge, and Beyond. It's sort of a, I don't know, go big, go home type of title. I mean, very open-ended, I suppose. I hope that I can live up to some of it anyway. If you have a question afterwards, if something's not clear or whatever, feel free to post them on Slido. I'll try to answer them afterwards, and if we run out of time, or if you come up with a question after we end here, I mean, feel free to come up to me afterwards. I'd love to discuss these ideas that are starting to penetrate the industry, and that are very much work in progress for us as well, and as in most people in the industry. So we can start with the state of the art of cloud infrastructure today. It's really good. It's very easy to take it for granted. It's almost hard to imagine what the world was before we had things like containers, Docker and Kubernetes and these type of things. All the great tools that the cloud providers have, AWS and Azure and GCP have allowed us to use. I remember when I started Akka about 13 years ago. Now, none of this existed. It was really hard to move to the infant that the cloud was. But the last 10 years has really improved rapidly. But it's not all good. All these amazing options and tools can sometimes be really overwhelming. It's very easy to drown in decisions, in options, in like the vast landscape of products. And this image here is, it's actually it sort of reads like a joke, but it's actually taken from CNCF website. It's how CNCF describes the cloud native landscape today. I mean, how can anyone make sense of this? I mean, sure, people are, but I'm sort of half joking here, but I mean, knowing what products to use for what and how to compose them is really challenging. It's just too much good stuff. All of these things are amazing products, of course, but how can we as customers or developers navigate through that in an intelligent fashion? It's actually quite hard, and many are still stuck. Or most are probably still stuck with an enterprise stack that they have to manage themselves, either on-prem or in the cloud. And that this means, this is actually probably a vast simplification, a drastic simplification of an architecture. But still involves load balancer, like an ingress router, some sort of API gateway. We have one way of caching. You have some framework to write your services or applications in. You have event brokers. You have probably more than one database depending on usage, etc. It's really hard. The serverless came about a few years back, with Amazon Lambda. And I remember when it came out, it was really revolutionary, I think. It really pointed towards the future in how we should build applications. But I think it's, at least for me, it's definitely not a product. It's not even a technology. It's not equal to function as a service. It's not the same thing as Amazon Lambda or Google Cloud Functions. It's an experience. It's how I think we all should develop for the cloud and the edge, as I will talk more about later. It's really the future developer experience, the future experience in how we consume and build for and deploy to the cloud. We shouldn't cut it short by just using it for function as a service, I believe. And serverless sort of brought this notion of zero ops, no operations. It's all on us. You just figure out the code and push it up to us, etc. And of course, that's a wonderful thing. It means we have more time to focus on the code or building real business value, and so on. And as I said, I think function as a service really showed the way here, but it also got stuck. It sort of got stuck halfway, because it only focused on communication, how to truly abstract very well over communication. You just have event coming in, event going out, and then you can write your little function that reacts to that. But it actually ignored one of the harder things, or one of the more important things, especially today, like real-time data-driven type of systems. That is the actual data, the state. Sometimes your applications need to be stateful. They can't just be stateless. And it also didn't fully abstract, and now I'm talking about function as a service. It didn't fully abstract over infrastructure, the way I think things could be done. And often, you're actually sort of left with sort of an integration project of lots of different APIs, products, etc. With the serverless FaaS right in the middle, doing a ton of great stuff, but still leaving it a lot on the table for us as developers to integrate with. So because even if so, a lot of products today call themselves serverless. You have serverless databases, caches, serverless message brokers. But even if all of these are serverless, it's still the sort of the job for us as developers, you and me, to integrate it all, to make sense of it all. As we all know, things usually fail in the intersection between things, at the boundaries when we need to do data handoff. Are guarantees actually maintained across these products? How can we make sense of all of that? It's non-trivial. So I think something that I've been thinking about the last years is really, can we do better? And then what lies beyond serverless? What is the next step after serverless? And just a couple of weeks ago, or probably a couple of months ago now, when I think about it, but anyway, I read this great article that sort of put a name for the thing that I'm after, that sort of we've been working on the last year, so trying to tackle, and that is vertical integration. You should read this article by Stephen O'Grady from Redmonk, an analyst firm. And one of the things that he said in this article was, and I quote, "There are already too many primitives for engineers to deeply understand and manage them all, and more arrive by the day." And even if that was not the case, there is too little upside for the overwhelming majority of organizations to select, implement, integrate, operate, and secure every last component or service. Time spent managing enterprise infrastructure is time not spent building your own business. I think this sort of summarizes really well the problem of having all this great infrastructure that we still have to integrate. And this calls for what he calls vertical integration, someone or something doing that integration for us. Words of wisdom here is like, I think this, the famous quote by Alfred North Whitehead is really apt, and it very much applies to software engineering here. That when I'm sure you've heard it before. Civilization advances by extending the number of important operations which one can perform without thinking about them. That sets us free to really go and execute on value if we don't have to think about all these other things. So I really think that we need to go from serverless to Yeah, need to come up with a new name. You know, what is databaseless? Is that even a thing? I don't know. Infrastructureless. I picked databaseless for this talk. You know, the last years we've been sort of moving from building systems on-premise, in which, as you can see the legend here, the red means that we as users need to manage everything ourselves. And the blue here is what managed by the operator or the cloud provider. In the cloud, you know, the cloud usually takes care of all these things for us, like the infrastructure, running Kubernetes, the operating system, the actual servers, etc. Really serverless in the sense. But I don't think this is any way near enough. It's still just too much of the red stuff, you know. I really think that what we need is this, where we just focus on the business logic, which of course includes the data modeling, etc. And the rest is on the platform, or the service, or the tool, or whatever you happen to use. And this is really vertical integration, where you integrate the stack vertically, and leaving as little as possible for us as developers on top to focus on. Okay. So I've talked a lot about the clouds. Now I'm going to dive into the second sort of aspect of what I'm talking about here. They both are, you know, equal lenses into what I'm trying to talk about. Edge computing. And I think, you know, we talked a lot about the cloud. I think edge is the natural extension of the cloud, as I will talk more about. And Gartner came out with his report in 2021 where they said a lot of things, but one of the things they said was that edge computing is actually being implemented today in many of our clients' environments, enabling entirely new applications and data models. Simply put, edge has moved from concept and hype into successful vertical industry implementation and general purpose platform status approaching rapidly. This very much echoes all the conversations that I've had and we've had at Lightman with our clients, that like many are already using the edge, if you're like forward thinking. They actually have been for some time, but often in some sort of ad hoc way. There's really no structured way of managing the edge or building applications for the edge. Many want to leverage the edge, but they don't know how. And I can say all of them struggling with intersection. Where does it move from cloud to edge, and how do you build? Do you need to build systems in a completely new way for the edge compared to the cloud? If so, I mean, I think it's really, really sad, because ultimately, you know, the challenges and the problems might be the same, but for us to be liberated as developers, we shouldn't have to think about them. They should be abstracted. Okay. So, sort of channeling my inner William Gibson here, if you're one of these old-time science fiction geeks, the edge the edge is already here. It's just not fully leveraged. I really think that it's a fact. You know, it's not just what I think. We have really great edge infrastructure today. Probably not everyone knows that. All the major cloud providers have had or have had edge clusters, sort of really small data center out on the edge for quite some time. And CDN networks are allowing us as developers to attach compute to the static data that they provide out on the edge. And the telcos is actually already allowing us to build applications that run inside the actual cell tower itself. And of course, 5G, you know, that's still a little bit around the corner, but it's already here. You know, we will radically change everything that we know, you know, around low latency and high throughput and serving the customers exactly where they happen to be at all times, and so on. So it's really, really exciting stuff. But all of these use cases, they demand, and customers demand, through these use cases, that we move data and compute to the end user. You know, we need to see data and compute as one thing, and it needs to move with the user in order to really be able to serve with low latency and high throughput, and also provide extremely high levels of availability, as we'll talk more about later. So I think, I mean, a lot of people talk about edge computing. I think we need to move beyond that and think about edge and data holistically out, sort of data and compute holistically out on the edge, and not just think about the compute aspect, and always have to go back to the back-end cloud and fetch the data that you can then compute out on the edge. It's just too costly. It's just too slow. Okay, and for those that are interested, there's according to this Gartner article, a huge market on the rise. Like from 4.6 billion in 2020, well, that would grow to 61.1 billion according to Gartner. They're probably wrong on this, but they at least probably right on the trend, I think. So some of the edge use cases that we've been seeing, we're working with our clients. Not all of these, but probably more than half of these we've already seen implemented at our clients. There are things like autonomous vehicles, like retail, like modernized retail, really close to where the user is right now. Trading systems, healthcare, emergency services, factories. They're able to operate without a connection to the back end cloud. Because factories can simply never ever shut down. That's extremely costly for them. Like things like stadium events, sport concerts, where you would that we're always, or most of the time, these the sort of the bandwidth will get really congested, and it's really hard to communicate. Gaming, farming, financial services, smart homes, that sort of goes into IoT. There's of course a subset of edge, and more. Another very important thing is this like tsunami warning that Gartner gave, that they sort of predict that by 2025, 75% of all enterprise-generated data will be created and processed out on the edge, compared to about 10% today. And of course, this is necessary for to be able to serve these massive amounts of data. We can't do data shipping, moving it all the way to the back end cloud, process it, and moving it back with the answers. You need to be able to intelligently give answers back to the clients right out there, right when it happens. So just keep the data out on the edge and do the processing right there. And of course the benefits are that you really are able to serve your customers extremely well. Real-time processing, extreme low latency, and really high throughput. And also, what most people don't talk about when they talk about edge is the resilience aspect of things. Because if you have data and compute right where the user is, you actually don't need the backend cloud for more than a nice to have, to do like batch processing overnight, to give more intelligent answers eventually perhaps. But if you have everything you need, the processing and the data, you can just directly do it out on the edge and return it back to the customer, which becomes a lot more reliable than today's cloud systems. And often, of course, they are hybrid, where you can sort of use the best of both worlds. So, but the edge means many different things for different people. The way I see it as sort of I'm sorry for this ASCII art I drew up. I didn't have time or the skills probably to write it and to do it any better, but hopefully it works. So this is the way I see the edge is a continuum. It's sort of in terms of layers. You have the backend cloud down at the like at the bottom here, but then you have sort of different type of edge layers that are closer and closer to the end user. The jury's still out on the terminology. Some people call these near edge, far edge. Some people call it regional and edge clusters. Most people have agreed on that there's actually the devices out there. But what is interesting is this is a hierarchical model, where you have more and more devices, more and more stuff, more and more data, more and more users as you go out, and that sort of consolidates when you move in. So that's sort of the mental model I'd like you to have here. Okay. The interesting thing is that each one of these layers gives new opportunities, right? So further out, if you should just try to sketch some of these here. This is of course not complete. But in general, further out, you normally have like tenths to hundreds of thousands pops. That means points of presences, like nodes or things, to coordinate and to make like function as a system somehow. Further in, it's usually like tenths to thousands, perhaps up to 10,000. It depends on where you sit in this layered cake. Further out, you usually have very unreliable networks and very unreliable hardware, while further in towards the cloud, you can count more on the hardware and to be reliable and work. Further out, you have very limited in terms of resources and compute power, while in the cloud, of course, you have vast resources and compute. You can just do whatever you like, more or less. Further out, you have real time. Further out, sort of lends itself a bit more towards real time and low latency processing, while for back towards the cloud, lends itself better to like batch processing. Is usually higher latency, not within the cloud, but up to the end user, of course. That's the perspective you should have here. Out on the cloud, you usually are forced to design your system in a way that take advantage of weaker consistency guarantees. While further down in the cloud, you can usually rely more on ACID, strong consistency, which simplifies things, of course, but it also means that we need different tools or different ways of looking at the data problem the further we get out towards the devices. Out to the devices, as I said before, you can usually do local compute. You can get answers directly out to the user very, very quickly, but the answers are less accurate because you have less compute power and you see more narrowly, of course. While in the cloud, you can see broadly on a global scale. You can make very intelligent decisions, but it takes longer, it's a lot slower, and so on. So that's why often a hybrid approach is interesting, like almost like this. If you remember this, what was it called? The Lambda architecture in streaming, where you have two layers, one providing answers immediately and another one doing batch processing, and they merge in the end. And as I said before, the further you get out, counterintuitively, you're actually more reliable because you have data and compute right there where it needs to be. You're less reliable from the perspective of the device. The further down in this layered cake you are, because the network can break, become unavailable, and so on. And it often requires more fine-grained replication to serve the users out on the edge, while you can get by with more coarse-grained replication and coarse-grained, more stationary data, sort of down towards the cloud. So this is sort of the mental model. It's both challenges and opportunities on both sides of the cake. We just need to make sure that we sort of leverage each one ultimately, okay? So what are some of the technical requirements needed to tackle this sort of new world in a way? Can we tackle them in a uniform and holistic way? Yeah, some of the things that I've learned the last 15 years building these type of systems, but even more lately, of course, when clients have really wanted to take advantage of these layers all the way up to the devices, is that your services and your sort of components, or whatever you want to call them, functions, if you look at them like that, but really they're really not functions because functions are actually inherently stateless, while we want them to be stateful. Anyway, they need to be autonomous and they need to be self-organizing. This is no surprise for someone that's been working with the actor model for some time. The actors in the actor model, becoming Erlang and Akka, that I've been using, are inherently autonomous and self-organizing, which makes these type of systems a lot easier to reason about. We need means to have physical co-location of data, compute, and end user. I've been saying this a lot, and this is sort of also something that's not well accepted in this industry. We still try to reach for as much stateless, some sort of like stateless compute tier and data down in the database. And that's great for a ton of use cases, but it falls apart the further out you get into towards the edge, I believe. And it actually never worked really, really well for all use cases in the cloud either. So, as always, you need more tools in the toolbox, and both stateless and stateful are really important tools. We really need an intelligent and adaptive placement of data, compute, and end user. Not just having them at the same place, but actually place them wherever they need to be right now. And that might change. Let's think about an autonomous cars, for example. The cars, they drive around and they connect to different cell towers. So the whole point, is lost if your data's still stuck over miles away because you happen to start your journey there. The data needs ideally to move somehow. It can probably lag a little bit, but somehow along with the car and how it's actually moving physically. Another very interesting thing that we've seen a lot of people working on in research now is local first cooperation. That you actually turn the problem around. Instead of having cloud and that you sometimes push data out, you actually invert the problem and see local is always first. Things should always work, regardless if I have a backend cloud or not. And if I happen to have a connection to a backend cloud, then I can leverage that. That's a plus. I can use that for backups. I can use that for more thorough compute and things like that. But if I don't happen to have that backend, connection to the backend cloud, I'm fine. And these are many factories are operating, as I said, etc. And we need to think more in terms of fine-grained adaptive replication, row-level type of application. If you think about database, instead of always replicating, the full table, as we've often used to when it comes to replicating RDBMSs and things like that. And we need consistency a la carte. Well, what I mean by that is that not all sort of data is treated equally. Not all have the same needs. Some is actually totally fine with eventual consistency. Some type of use cases works very well with eventual consistency because it's actually how we think about the problem in the physical world. Why shoehorn that back into strong consistency then? The only thing you will do is add more latency, making things less available. But for some use cases, you absolutely want strong consistency. So we need model, frameworks, tools to give us choices, give us options of choosing between these, without overloading us, of course, with information and decisions. And options for different type of state models, that you define the shape of the data, and its consistency model, and that's it. And of course, it goes without saying, providing end-to-end guarantees across different, products, all the way from the user, all the way through the stack down to the database. Unless you can provide end-to-end guarantees, you really know what you're doing or dealing with. So this is extremely important. So what is my vision of this sort of a cloud-to-edge data plane, if that's a good way to describe it? I really believe that it needs to be seen as a continuum, not two different things. Because where do you draw the line there? In which layer do you draw the line? This is the cloud and that's the edge, etc. I mean, we really need to be able to provide to write these services and have them run anywhere. In the public cloud to start with, or and then eventually perhaps being moved to thousands of POPs at the edge. The important thing is that it should not be a development decision. Definitely not. We can't hard code that based on the design patterns and tools, because that's then we need to rewrite it again when we want to move to the edge, or vice versa. It should not even be a deployment decision, I think, because these systems are adaptive, and you don't know what your clients will do, and you don't know how the use cases will evolve. Instead, why not let's simply deploy into this data plane and then having the runtime figure out, okay, now it's actually better to move the data and compute over there instead of having it here, etc. And that's of course include all these layers, moving it between the layers seamlessly. So instead, what if the only thing I need to worry about is that, what if my data just existed, wherever it needed to be? So always co-located with the service, with the end user, and with compute, where data is always there, it's always available, it's always correct, it's always where it needs to be. It's automatically shuffled around, and it's injected into your service, timely, and intelligently. So your service always has the latest data, regardless where it happens to currently run. And not for any longer than it needed, because if it sits on the data longer, that causes problems. Then you sit on more resource than you really need, etc. And this, can really provide a platform for really ultra low latency and take full advantage of the cloud and the edge and everything in between. So, so this is sort of the mental model I have. This is the vision I'm going towards. Let the data just flow wherever it happens to be needed, and not any longer where it actually need to be. And one big question then: how do we find the right abstractions for this? As Timothy Keller said, freedom is not so much the absence of restrictions as finding the right ones, the liberating restrictions. Constraints can actually be liberating. And if the work that we've been doing the last years is to start with that problem. So trying to distill what is really the ultimate programming model for tackling the cloud to edge continuum. And I think I've sort of come down to three things that I think developers can never really delegate. First is the data model. How to model our business data. Its structure is constraints, its guarantees, the way I want to query it, etc. Second is the API. How do I want to expose myself to the outside world? What kind of data do I want to make available? How do I communicate with other components, etc. So both service to service and service to the world type of communication. And finally, the business logic. How should I mine that intelligence? How should I be able to react and respond to requests and events coming in? What should I emit in terms of answers, etc.? How do transforming, downsampling, relaying events and things like that. And of course, using multitude of patterns, things like workflow, point-to-point, streaming, etc. Not too many, but the right ones. But apart from these three, I think the rest should actually be fully managed and outsourced to the underlying platform. Because that's not where the core value is for us as developers. That's not the core developer experience that I would like to have, at least. So the last years we've been working on a product that we're just about to launch. Actually, it's actually not fully out under this name. We've had it out as Akka Serverless earlier, but now, which was sort of a code name for it, more or less. But we're launching this next week. Is in a fully managed developer PaaS for building real-time event-driven type of systems, like spanning both from the edge and to the cloud. And we're really trying to move then beyond serverless in databaseless or infrastructureless territory, where every single thing that you need to do can be declaratively configured apart from the business logic. And everything, databases, event brokers, API gateways, everything is like on us, that you never have to see that. It's how those are configured flows out of how you configured your services, and that's it. Okay. It's fully polyglot. For a lot of people that have been following Lightbend knows Scala and Java was our only options here. Now you can actually use it from almost any of your languages that you might have as favorites. Supported, we have Java, JavaScript, TypeScript, and Scala, but we have Python and Go and many others in the works. And we're really trying to tackle this problem of unifying cloud and edge deployment into this in this cloud to edge data plane. And it's reactive at its core. It really is built on Akka, it's built on Kubernetes, it's built on gRPC, Linkerd, and many other great components, but you never see them, really. The only thing that you can, if you're an Akka developer, you will see it through the way we deal with the problems, more from a design perspective. So if you remember this picture, this is really Calyx. It's infrastructure, it's vertical integration as a service. So what many of you might wonder, okay, what will it then look like? So let's take a look at some code, how you would actually build a service using this model. The first thing you would do is write an API description. Calyx is a schema first. So you do most of the things declaratively first, as I will show you. Then you define also declaratively the state model. What kind of shape does my data have? What kind of consistency guarantees do I need it to have, etc. And then finally, you just write your business logic, and that's it. The rest is on us. So let's take an example here. Step one, define the API in data. In this little example, I'll try to show what it will take to implement a small shopping cart. I'll provide a link at the end, where you can go if you want to learn more and see this example in action and try it out yourself. But I don't have time for that. I'm just going to go through the essence of how you do it. First, it's schema first, as I said. We chose protocol buffers to define the schema. We will definitely provide more options later. We're looking at like annotation based now. We're looking at perhaps providing open API type of spec. That doesn't really matter. The important thing is that it's declaratively configured, and out of that flows the rest, so to speak. So in this little example, we start with defining a command, sort of a request, add line item in this protobuf specification or schema. As you can see here, we annotate the user ID with the entity key, and this means that it will be the primary key for this service, which is extremely important because that's what's used for things like looking it up for, of course, doing querying with the views that I'm going to show you later. It's used like for doing efficient cluster sharding, adaptive placement of code and data. All of these like flows out of this entity key, which is really important. Then we define a little shopping cart here. The first thing we do is, of course, is to define like service shopping cart. That's like protobuf way of defining that component. But then we add a little RPC method. In this case, add item. It takes one of these add line items, returns nothing, and then the only thing I need to do there is actually that really. Here I have optionally added one of these protobuf annotations that says Google API HTTP, where I can provide a hint to also generate, apart from gRPC, which protobuf natively supports, I can also generate HTTP endpoint here. And that's why I can provide now like a post URL here. And as you can see here, you do provide the user ID here. That is the entity key. Here I can also choose to add another option on sort of a hint on how to what kind of code to generate here. In this case, eventing. I can sort of define an in event stream and an out event stream. The in event stream is my event log flowing into the shopping cart. My out event stream, I choose to define a topic here, shopping cart events. So all this is declaratively configured. The second thing I want to do is also declarative. I want to define my state model here. So regarding the state that I defined here, what kind of shape will it have? So to speak. We provide different type of state models here. More will be added, of course. But now out of the gate we have event sourcing, we have key value, we have data structures and views, which I'll get to in a second, which is like a query type of model, state model. And the only thing I need to do to switch between two of them is actually to change this single line of code. So that's also a hint in what kind of shape I want to view my data model. Here I can also define a materialized view, and that is done by simply first exposing an endpoint, an RPC endpoint. I call it get carts here. That returns, as you can see here, a stream of carts. And here I can choose to add this hint to generate a materialized view, an adaptive, fully sort of streamed a materialized view using this SQL style quick query that actually works directly on your domain data, but is of course backed by database. So here I'm interested in selecting all cards that has a specific user ID, a very simple view. And finally, I can also then choose to expose this endpoint as HTTP if I want to be able to query it, and then updates to this view will be automatically propagated and pushed to this endpoint. So that's everything I need to do. Define my API, my state model, my eventing, what kind of endpoints I'd like to expose, all declaratively done. And then finally, it's time for me to write my business logic. And here I can choose whatever language I happen to want to do, out of the supported ones, of course. Here I choose JavaScript. And this is essentially almost everything that you have to. This is a little bit more boilerplate just to wrap it, with some imports and stuff. But more or less, I'm registering here a command handler. What should I do when I receive this add line item request then? And then I write this little function. And the interesting thing here, which is fairly unique, is of course the event is injected, just like classic functions as service serverless style. But you also get the state injected. Here you can be guaranteed there's always the latest state, there's always what you expect, it's always correct, and so you actually never ever have to go down and fetch the state from a database, from a cache, wherever. It's automatically injected as needed into your function. And you also inject the little context here, so you can just for doing some extra operations if you would like. That's it essentially. So I think take a step back. I really think sort of one of the key innovations here is that, as I said before, as in FaaS, not just the events are injected into the function and that you can just emit without caring about how it's relayed and how it's persisted and everything. We do the same thing with the state as well. So the state is injected, and when you're done with the state, you just emit it, and the rest is on us, really. So it's really completely managed for you, in as lazy way as possible, of course, because you don't want to use more resources than absolutely needed. So the problem, is with if you don't look at state this way and still want to go all in on serverless, meaning abstracting across all infrastructure. The problem is that if the function manages the state, it's really a black box to the runtime. It can't look in unless you do code introspection, and bytecode munging if it's Java or whatever. The runtime can't see what you're doing if you define the queries, if you manage the state internally. So this means that unconstrained database access from within the function makes it really hard to automate things and do things as efficiently as needed, because it's really hard to understand the intention of each data access. Is the operation a read? Is the operation a write? Can it be cached? Can consistency be relaxed, or does it always need to be strong consistency? Can operations proceed during partitions or failures, or is it the stop the world? Failure scenario. And if the runtime can understand the answers to these questions, it can more efficiently optimize things, not just your service, but the system as a whole. Like how data should be replicated, where data needs to be ahead of time, and things like that. For example, if write operations are really fast and read operations are really slow, add more memory to the database. If you're always reading immutable values, you can safely use caching. You never have to hit the database at all. And if for example, if writes can be serialized, if writes must be serializable, then you can add sharding. Single writers per entity. So really, if the runtime, the platform knows these things, it can make a lot more intelligent decisions, which I think is needed in order to operate across all these layers in the cloud to edge continuum. So just a few words, how, because some people might wonder, what does it look under the hood? It's really nothing that a user would need to see, but still it could be interesting to know. So it all runs on Kubernetes. It's really platform agnostic when it comes to cloud providers. Now we're on GCP and AWS, and Azure is coming soon. We have what is called an execution clusters. There can be many execution clusters. We have one management cluster that you go into to manage it. But many execution clusters that can run on any sort of Kubernetes cluster, wherever it happens to be. You have the notion of a project that has a service. And here's the interesting thing. I mean, each user code, each user function, is proxied by a sidecar. We sometimes call it a sidecar. We sometimes call it a state proxy. So what this means that if a request comes in from the outside, it will hit our gateway, in this case Linkerd, that will then relay that to the proxy that acts on behalf of the user code. Everything's always passing through the proxy, which means that it can always like optimize communication as good as possible, inject all events that needs to be that sort of flows to the service, and also accept and continue to emit all the events that are emitted from the service. But also state, it can keep state fresh, it can keep state consistent, as lazy as possible, and move state around these sidecars. So wherever the function happens to run, it will always be injected with the right state. So it's a classic sidecar type of architecture, but all powered by Kubernetes and Akka cluster. So in summary, I really think that cloud development today is too complex. There's too many options. There's too many things that need answers, and can be overwhelming. And especially when you need to start composing things, it's really, really becoming hard. Serverless is really, really promising. The serverless experience, I would say, not serverless the products. But I think it actually currently falls short, because it still leaves us with an integration project of all these APIs and products that all happen to be serverless, but no one takes the responsibility of bringing it all together and providing a full serverless experience, if you understand what I mean. We need vertical integration to do that. The other aspect of things is that edge computing is already here. Perhaps not for you, but trust me, in like 2 to 3 years it will be, because it's less too good to not take advantage of. The cloud provider is starting to roll out data centers. You can, working with the telcos on making most out of 5G, and it's just so many new opportunities. It's just too good to not take advantage of. Your customers and clients will want you to do that. I really think to tackle this well, we can't see the cloud as one thing and the edge as one thing, and use different tools for different things. We need to see it as a continuum, and sort of have a model that allows us to intelligently tackle all the challenges without sort of changing the way we write the code or deploy the code and design, of course. And Calyx is our modest effort to try to tackle this. It's early days for the product. It's all built on open source software. Sort of please let us know what you think. I'd love to hear feedback both from this presentation afterwards, but also if you try it out. I think you will like it. If you want to learn more, go to docs.calyx.io to dive in and try it. And we have forums and everything, so don't hesitate to reach out and tell us, especially what's bad, because that's ultimately what I want to hear. Thank you. So we have some questions here. I only have 1 minute, so. How Calyx support distributed relational databases is one question. The thing is that we run on distributed databases. I mean, there's no secret that we, for example, we chose to we sort of along the way we've been running on many. Now we sort of chosen Yugabyte to run on. It's a really good distributed database. But the whole point is that you don't need to care. We could switch this to Cockroach, tomorrow, and you wouldn't know. The durability guarantees, the consistency guarantees are all the same. For many of the type of replication mechanisms, we actually don't use a distributed database at all. We use Akka in-memory replication, and sometimes, you know, even sort of storage on disk, but without hitting the database, because, you know, we simply don't need to hit the database every single time. But the point is that that it's all abstracted. We pick the right database for the job. When we add more state models, for example, if we would like very likely to add a graph state model, for example, then we'll of course, you know, pull in the graph database. We're thinking a lot about, you know, doing more with streaming now and things, and that will call for another type of storage model probably, and so on. So that's it. Isn't vertical integration application server ID all over again? That's a good one. Perhaps I've never thought about it like that, but in a way, you know, what application servers did really well was abstracting all these layers that you didn't have to think about. You know, it didn't do it that well. I don't know, like container managed persistence in EGBs wasn't the best thing, even though I was really hyped about it when it came out. You might be too young to remember these things, and bless you for that. But really, it's. I think the main difference is that application servers were monoliths. They weren't, you know, built to tackle any type of distribution well. I think, of course, you had, you know, abstracted sort of distribution when it came to EGBs, or, you know, through using RPC and all of these things. But it wasn't really made for the world of the cloud. Even honestly, I think that's why we saw things like Akka and Vertex and other types of tools come out about 10 years back. But I don't think these tools really are up for the job either, because they're too, you know, often too hard to use. I mean, Akka is amazing, I have to say. I'm biased, of course, but it's often too low level to really build systems very, very fast. It can sometimes give you too many options. It might sometimes be too powerful, and that of course holds for both Vertex and Quarkus and many other things. And that many people love to build, you know, cloud-native applications today. So I still think that even though these things are great, it's not the end of the story. We need to climb the ladder of abstractions, adding more and more good things on top, and leaving as much as possible for others to solve well, so we as developers can focus on building value for our business, hacking code. So I think that's all the questions I was able to go through in time. But don't hesitate to grab me. I'll be here for this afternoon. I'd love to have a chat. Thank you.